Frontier Center ผู้อำนวยการของ Gravitational Waves and Cosmology และหัวหน้าภาควิชาฟิสิกส์และดาราศาสตร์มหาวิทยาลัยเวสต์เวอร์จิเนียในประเทศสหรัฐอเมริกาค่ะงานวิจัยหลักที่ดร.ลอร่าสนใจเกี่ยวข้องกับการศึกษาดาวนิวตรอนและสภาพแวดล้อมผ่านการสังเกตการณ์ในย่านความถี่วิทยุเอ็กซเรย์และรังสีแกมมาจุดมุ่งหมายสำคัญของการวิจัยคือการใช้ดาวนิวตรอนในการตรวจจับและจำแนกลักษณะคลื่นของความโน้มถ่วงที่ความถี่ต่ำผ่านการจับเวลาของเครือข่ายของพอซ่าที่หมุนด้วยความเร็วระดับมิลลิวินาทีซึ่งมีความแม่นยำสูงเป็นพิเศษนอกจากนี้ท่านยังได้รับเลือกให้เป็นนักวิจัยที่มีการอ้างอิงสูงที่สุดในปี 2536 และปี 2535 โดย Web of Science ซึ่งเป็นหนึ่งในรางวัลการวิจัยชั้นนำของโลกผลงานของท่านยังได้รับรางวัล Alfred P. Sloan Fellowship Portal Scholar Award จาก Research Corporation และ ABS Fellowship ในปี 2564 ดร.โนรายังเป็นผู้ร่วมค้นพบ Fast Radio Burst หรือ FRB ดวงแรกซึ่งทำให้ท่านได้รับรางวัล Shaw Prize ในสาขาดาราศาสตร์ในปี 2566 นี้ด้วยค่ะสำหรับในคืนนี้นะคะดร.โนราจะมาบรรยายในหัวข้อตามล่าหาหลุมดำด้วยหอดาวขนาดใหญ่ขนาดเท่ากาแล็กซี่ค่ะ Good evening, ladies and gentlemen. Welcome to NARI's special public talk. My name is Rapapa Sakasa, and I will be your host tonight. It is my pleasure and honor to introduce tonight's speaker. Dr. Maura McLaughlin received her bachelor degree in 1994 from Pennsylvania State University and obtained a PhD in 2001 from Cornell University. She is currently a very distinguished professor of physics and astronomy, co-director of the Nanograph Physics Frontier Center, director of the Center for Gravitational Waves and Cosmology, and chair of the Department of Physics and Astronomy in West Virginia University. Dr. Maura's main research interests involve studying neutron stars and their environments through radio, X-ray, and gamma-ray observations. A significant research aim is to use neutron stars to detect and characterize low-frequency gravitational waves through timing an array of ultra-precise millisecond pulsars. She has been named a 2020 and 2022 highly cited researchers by Web of Science, one of the world's top research awards. She has been awarded an Alfred P. Sloan Fellowship, a Portrait Scholar Award from the Research Corporation for her work, and an APS Fellowship in 2021. Dr. Maura is also the co-discoverer of the first fast radio burst, or FRB, for which she was recently awarded the 2023 Shaw Prize Award in Astronomy. Tonight, she is giving a talk on detecting monster black holes with galaxy-sized observatory. So without any further ado, please welcome Dr. Maura McLaughlin.
Thank you very much. It is really great to be here. I'm wondering, let me see how to get my slides up. Will they come up automatically? Oh, there they go. Great. Thank you so much. Hey everyone. So it's really wonderful to be here. I was last in Thailand about 10 years ago or so for a scientific meeting. I've never been to NARI before. The facilities here are just completely amazing, and I'm really impressed with all the astronomy enthusiasts who have come out for my talk tonight, so thank you for coming. I'm going to tell you about a really exciting scientific project where we are using ultra-precise cosmic clocks called pulsars to detect invisible ripples in space-time called gravitational waves using the world's largest radio telescopes. Before I do that, just a little bit about me. You already heard a lot about where I've been and what I've done. This is the institution that I'm at. This is West Virginia University in the state of West Virginia in the United States. I've been a professor there for about 17 years now. I live close to the Green Bank telescope. This is a 100-meter radio telescope. It's the largest radio telescope in the United States. So West Virginia is a really great place to be to do radio astronomy because we have this amazing telescope in our backyard. My husband, Duncan Lorimer, is also an astronomer. Here's a picture of the two of us on top of this telescope, and we were just both in Hong Kong receiving the Shaw Prize for the discovery of a new class of astronomy source called a fast radio burst. And I'm not going to be talking about that today, though. I'll be talking about something completely different, which is this gravitational wave detection experiment. Here's my son, Owen. It's a little dark. You probably can't see him, but he's sitting over there, and he's been along on this trip with me, which has been really fun. Okay, so to talk about gravitational waves, we need to just first start with gravity. I see lots of kids in the audience. How many of you have learned about gravity in school? Okay, so I remember when I was your age and we first learned about gravity, we thought of gravity as an invisible force, right? So it's a force that makes apples fall from a tree, it makes the moon go around the earth go around the sun, and we learn laws, we learn Newton's laws. If you're a little bit more advanced than you've taken physics classes, that will help you model the effects of gravity. So massive objects feel forces from other massive objects, right? And so we have this idea in our head about gravity. And it works in almost all situations, except when you have very massive objects moving very quickly. How many have heard of Albert Einstein? We've all heard of Albert Einstein, right? He's a very famous scientist. So he came along in the early 1900s, about 100 years ago or so, and he said, you know what, I have a completely new model for gravity. We're going to get rid of that invisible force, that F equals ma stuff, and we're going to think of gravity as a geometrical construct. So Einstein's idea is that we are all living in four-dimensional space-time, so 3 spatial dimensions and 1 time dimension. And if we have massive objects, like the Earth here, the Earth will distort the shape of the space-time in which we are living. And the reason that the moon goes around the Earth is not because it feels this invisible force. We don't need that invisible force anymore. The moon goes around the Earth because it has to, because it's sitting in this curved space-time. It's just following the shortest possible path in this curved space-time. I noticed downstairs in the museum there's a black hole, one of these like plastic black holes, and you can put a coin in and it goes around and around. How many people have thrown coins into that black hole? Okay, yeah, so this is the idea, right? So if there's a black hole or an object, the space-time is curved around it, and objects have to orbit it because of this concept. And this is called general relativity. Okay, so imagine that we have 2 objects. So we have 2 stars, or the Earth and the Moon, or 2 black holes, it doesn't matter, 2 objects that are orbiting each other. If they both are sitting in their own little gravitational wells, right, as they orbit each other, they will cause waves or ripples in space-time. So binary objects that are in orbit around another object, will cause space-time to ripple. And these are called gravitational waves. So these are ripples in space-time. They carry energy away from pairs of objects. So these objects are going to get closer and closer and closer together because they're losing energy due to these invisible ripples in space-time. And what these ripples do is they change the distance between objects in space-time. So let's look at another little movie here. So this is the Earth. Let's look what happens when these 2 stars eventually collide into each other. Okay, when they collide into each other, they're going to emit a huge burst of these gravitational waves, a really big ripple that's going to travel throughout the universe. Oops, let me go back. Okay, I'll get there. Here we go. Let's see. Okay, here we go. I was too over eager. So the gravitational waves coming from this binary system that's collided are traveling through the Earth. As the 2 stars get closer and closer and closer together, the frequency gets faster and faster and faster, and then they collide. And this actually is happening to the Earth all the time, right now. All of these cosmic collisions produce gravitational waves, and the Earth is wobbling and shaking all the time in exactly this way. Of course, this is greatly exaggerated. Bubbles are much, much, much smaller than this little cartoon obviously would show, but this is happening all the time right now. For those of you who want like a more scientific explanation of what gravitational waves do, if we have a ring of test particles and a gravitational wave would come through the screen, it would perturb the distances between the particles in this very special way. We call this a quadrupolar pattern because there's sort of like 4 points to this perturbation. So this is what a gravitational wave would do to particles if they were in a circular ring and the gravitational wave traveled through the screen. So this is what gravitational waves do. Okay, so let's talk a little bit about how we can detect these gravitational waves. So we can't see them, they're not light, they're totally invisible. They change the shape of space-time, but on extremely tiny scales. Like we can't just feel it, right? So we need very sensitive instruments to detect them. People have been trying to do this for many, many years. In the early 1960s, this guy named Joseph Weber built this like really giant metal bar, and he thought that as a gravitational wave went through the bar would vibrate, and he could detect these vibrations. He wasn't able to do that. A couple other experiments were built, and they were unsuccessful until something called LIGO, the Laser Interferometer Gravitational Wave Observatory. This was started to be constructed in 2001, and this is how it works. So this LIGO detector has 2 arms, and these arms are perpendicular to each other. They're at a right angle, and lasers travel up and down across these arms. And when a gravitational wave passes through this detector, one of the arms gets a little bit longer and one gets a little bit shorter because of this quadrupolar gravitational wave perturbation. And so when one arm gets longer and one gets shorter, then the light takes a different amount of time to travel than it would if there wasn't a gravitational wave. And this is detected in an interference pattern here. Okay, so this is like a little complicated, this wave interference. But the really important thing you need to remember is that LIGO searches for very small changes